My apologies for being a bit late because the simplex tableaus took me a bit longer than I expected. But we don't have a lot to cover, in fact. So there's no rush. Okay, so what were we talking about last week? Anybody remember? Yes, correct. Manchester rain. Yeah, I can use that. Fermentation groups. Okay, so today the program should be and will be and is Dihedral groups. And you know what they are, don't you? Was I supposed to bring you anything? No. There's a handout from last week, the reading notes and exercises, so I don't need any.
Yeah, Kevin had to correct me because I said, "Oh, what's that chapter on cossets?"
Is it pronounced cosets?
It's cossets.
Is it some sort of set that contains all the...
Probably.
Yeah.
It looks like cossets and had a tone of voice like you're an idiot. It's cossets.
I mean, you got killings.
Yeah, very much.
Yes, you will be doing cosets with killing.
I know how to pronounce it actually.
Step one for the... Get able to say it.
Okay, so you know what dihedral groups are? There are, how many dihedral groups are there?
2.
No. Yeah, infinitely many.
It's very different from mine.
Because they are, each of them is the group of symmetries or whatever, rigid motions, as this book says, of the regular n-gon. And you can have n from 3, 4, 5 to infinity, excluding infinity. Okay, so we know what they are. So the nth dihedral group the n is the group of symmetries of the regular n1. Is it readable? Okay. So let's, which n-gon can I draw? Okay. Hexagon, okay. The heptagon, I'm not sure I can draw. So you can view this group as, well, in fact, what does it actually mean? So it's before we tell you what isomorphism of groups is, we're slightly on thin ice, because you have groups that, well, being isomorphic means that the groups look the same, but they're not the same, strictly speaking. I don't know if I could give you an example of, okay, I don't know. I'll just put a very stupid side remark. Okay, you remember graphs as something with vertices and edges, networks with, sometimes they're called nodes. Vertices. Okay, so if you have vertices called 1, 2, 3, and 2 edges 1, 2, and 2, 3, you have a graph. Okay, now I'll draw a completely different graph. Okay, this is now a completely different graph, because the top one has a vertex 1 and the bottom one doesn't have a vertex 1, and the top one has a vertex 2 and the bottom one doesn't have a vertex 2, and in the top one there is an edge between 2 and 3, and in the bottom one there is not an edge between 2 and 3, there is an edge instead, there are no edges between 4 and 5 and 5 and 6. Okay? So strictly speaking, when you're looking at it as what it is, some set of nodes and some set of edges, they are different. However, to all purposes that you can think of, they are the same. And that's called isomorphism in mathematics. This concept of two things that just have different names sitting on the elements of it, really. They're called isomorphic. And it's a concept in mathematics which appears everywhere. So this was an example with graphs. And with groups, you can have similar things. So if you take a permutation of the set 1, 2, 3, 4, okay, and a permutation of the set 7, 8, 9, 10, these things can't be the same because as functions they are different. One function has 1 in the domain and the other one doesn't. Okay, but for our purposes, the group of permutations of 1, 2, 3, 4 and the group of permutations of 5, 6, 7, 8 are really the same because the structure is the same of composition of the permutations and things like that. And here, the dihedral group you can look at in several different ways as well. Okay? So one of the ways is you really look at the hexagon as a concrete geometric shape, and then symmetry is something that for every point in this shape tells you where you map it. Okay? So think of the reflection along the vertical axis, and so it fixes these 2 points, but also fixes anything on this axis. And for any point in the hexagon, so the hexagon is really to the whole shape, for any point, you know where that point is reflected to. That's one point of view, how you can view the dihedral group. It's really just mappings that whose domain is the whole hexagon, and for every point in the hexagon, it tells you where it is mapped to. Okay, so that's one point of view. Another point of view is you just look at the vertices of the hexagon, and you take it as a finite permutation of these vertices. Okay, so 1 maps somewhere, 2 maps somewhere, 3 maps somewhere, and so on. So the vertical reflection in this point of view, so e.g. D6, we have this reflection, I'll call it S for some reason, and you can write it, in fact, as a permutation of the numbers 1, 2, 3, 4, 5, 6. And so 1 goes to 1, 4 goes to 4, but 2 goes to 6, and 6 goes to 2, and 3 goes to 5, and 5 goes to 3. So this is the cycle notation for this permutation. Okay. And then there's another element in this group, which is, well, more than this, there are 2 important elements in the group. And the other one is the one that rotates the hexagon by 60 degrees. Okay, so 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6, and 6 goes to 1. This cycle. Okay. And then, of course, you get all various other symmetries. How many are there in all? So, order. Because 12. It's either 6 or 12. Okay, so yes, the one way to see is this vertex 1 has to go somewhere. Okay, and it has 6 different possibilities where it can go. And then this vertex 2 has to go to an adjacent vertex, to a neighboring vertex, but it has 2 possibilities where to go. It could either go in the same preserving kind of orientation or reversing the orientation. So 1 goes to 4, then 2 could go to 3 or to 5. So it is, indeed, there are 2n elements in this dihedral group. And what else am I supposed to tell you? And there are kind of special. Yeah. So let's see all 12 elements. Okay, so we've already seen. So let's start with rotation. So we have this first rotation, which we've just seen as a cycle like this. And there's a second rotation, which is 1 goes to 3, so plus 2. 3 goes to 5. 5 goes to 1 again. Okay, so that's 1 cycle. So where does 2 go? 2 goes to 4. 4 goes to 6. Okay, that's the one. Then we have the third rotation, starting to be boring. 1 goes to 4, and 4 goes to 1. 2 goes to 5, and 5 goes to 2, and 3 goes to 6, and 6 goes to 3. Okay.
1 to 5, 2 to 6, 3 to 1.
1 to 5.
Yeah, 2 to
and
6.
5, 2, 3. You have to be. You have to go.
Yeah.
You have to continue. 1, 5, 3, 2, 6, 4.
Yeah.
If you're doing the cycle notation, you can't jump to 2 before you get there. Okay. 1 to 6, 6 to 5, 5 to 4, 4 to 3, 3 to 2. So these are all the kind of orientation preserving rotations. 1 is missing.
The identity.
And then there's S, which is pick a reflection. Okay, so we've done 2, 6, 3, 5. And I've purposely written it at the back, at the bottom, because the remaining are SR1, SR2, SR3, SR4, SR5. Okay, maybe that wasn't very smart. No, I don't think Killian can see anything with all the light. And you can't, you probably can't see anything like that. No, Killian's not watching.
Yes.
Maybe that one is the problem. So let's just try. I mean, maybe I've done it. I've probably not done it in the most convenient order. But okay, so if I do SR1, which means I'm doing R1 first and then S. So where does 1 go? 1 goes to 6, because 1 goes to 2, goes to 6. 6 goes to 1 goes to 1. 2 goes to 3 goes to 5. 5 goes to 6 goes to 2. Okay, so that's this one. And 3 goes to 4. Stays at 4. So it has to be this.
What did you say then, Jan? You're doing R1 first, then S, or S, then R1?
R1 first and S. It's a matter of convention. I think we agreed on composing permutations where we're reading right to left, unlike Sage. Okay, and then as an exercise, you can fill in those and you get all of the Okay, now, what else do you need to know about the Dihedral group? Okay, so when you take, we've picked one. So of course there are more reflections than just this one. There is a reflection around this axis, but you can write it. As the product of some of these. Well, it would be. Something here. So what's it going to be? So 2 and 5 stay put, and 1 goes to 3. Okay, I don't think we've listed it here, but it must be one of those. Okay. Anyway. Yeah. Okay, so we'll go to the next thing. Next thing is the group is generated by these terms. So if you have any, okay, so that's like I'll put it as an observation. The N is generated by the rotation by 1. Okay, so this is where 1 goes to 2, 2 goes to 3, and so on. It's just the basic rotation. And S, which is, well, any reflection will do. Not any rotation here we do. If you look at the hexagon and you do the rotation by 2, and then you don't get, in any way, you can't get the rotation by 1. Just so you get half. You get a subgroup. If you took the rotation by 2, you get a subgroup of half the size of the whole group. Okay, and okay, this is a note here. So what we've we've had 2 points of view. And one was permutations of 1, 2 of this set, just the vertices. And the second one I briefly mentioned was sort of symmetries of the whole shape. Okay, not polygon. It's a reminder. But now there is a third point of view, which is theorem 23, is that it is the group of, well, Dn is the group generated by two elements, R and S, that satisfy this. R to the n is the identity, S squared is the identity, and SRS is R inverse. Is it still? Okay, this is a bit of a fancy theorem, I think. So is it clear what it says? No. Not really clear, because again, I'm kind of cheating. I should say, giving you the whole truth with normal subgroups and congruences. But we'll get to normal subgroups and congruences later. So this is just a taste. And then when it comes up, you can recall dihedral groups. So this is a kind of, okay, I'll make a, okay, firstly, so when we look at it as a theorem, it should have a proof. So, but it's not clear, it's not quite clear to me. Okay, so the proof should be, I mean, kind of proof, is that we can take, well, exactly what I said. So R will be the 1 to n rotation, and S is the reflection that fixes 1. So reflection that fixes 1. 1 is, fixes means it's mapped to itself. It's quite a common expression. So first we should satisfy ourselves that these conditions really hold. So if you take the rotation by 1 and repeat it n times, then you get back to where you started, and 1 will be back on 1. Okay, so it does hold. Now, well, R to the n is 1. If you take a reflection and do it twice, you get what you started with. So that is true. What's the last condition? What does that say?
you doing it in your mind?
Yeah, that's what I asked for.
I was going to say something like smart.
Okay. Okay, I have this rotation as R. If I do it 4 times, I get back to where I started. Okay, now what happens if I reflect? Oh no. Reflect, rotate left, reflect. Rotate it to the right. I'm starting with 1 at the top. Okay. Reflect, rotate left, reflect. 1 is moved to the right. So this means this really says that you can, if you want to reverse a rotation, you reflect, do the rotation, reflect back, and you get the inverse rotation. Yeah. Another point of view is okay, I'm rotating left, right? No, you should say you're rotating right. Because I'd see it like this, but you see it like okay.
The lamb's mind's just been blown.
It's mind blowing. Okay.
So, I just got him holding his hands and he just does that and looks at him like that.
Okay. But well. Yes, well, what's missing? So, of course, yes, we have. What's missing is that any element of the group can be generated like this, but it can be. Any rotation where you preserve the orientation, okay, is just a suitable multiple of this rotation, and any rotation where you don't is like flip. And rotate. And wherever the 1 comes to, then. So if you get any. Also, every element of the n is either r to the k for some k, or r to the k times s for some k. So we basically know everything about dihedral groups now. Okay, I'll make a note here because it's an important. It's just one particular example of an important phenomenon. Okay, so I'll put it a note. It's not in the book, so listen. There is so if I give you a finite number of elements, or letters, whatever, then what I call the free group f of s generated by s is the group of all strings of letters in S. And their inverses and the identity. Okay, so now for example, if S is your AB, then well, Fs is an infinite group, so I can't list all the elements. Whose elements look like this. Well, the identity. A squared, A cubed, and so on. A inverse, A to the minus 2, A to the minus 3. So A to the minus 3 is take the inverse of A and multiply it with itself 3 times. So what you would expect. Same for B, B squared, B inverse. But then things like A, B inverse, A squared, B squared, B, A, B inverse, A cubed, B to the minus 4th, and so on. So all these kinds of things you can create, and this gives you a group. It gives you a group. Why does it give you a group? Well, because it has some identity, and when you multiply them, then you just multiply them. So how do you multiply in this group? For example, if you take AB squared, A inverse, B cubed, and multiply it by B, A inverse B, then what do you get? You get AB squared, A inverse, B to the 4th, A inverse B. Because these two form the B to the 4th. Okay. And if you want AB, A inverse B squared, and multiply it by B to the minus 2, A, B inverse, A inverse, what do you get? Yeah. Okay, so this is a free group. This gives you a way of creating the inverse for every element, any element in the free group, and so it's clearly a group. Now, the note continues, and it says that a finite presentation of a group is a finite list of well, I would say identities, but identity would be confusing because the identity is an element of the group, but a finite list of equalities yeah, that define the group. Okay, this is so without getting too technical, I'm just giving you these notions in an intuitive way. So for example, you could have a list of things that says r to the 6th equals the identity, s squared equals the identity, and SRS equals r inverse. Right? So this is the sort of equalities that you're given. And then you say, let's take a group which is generated by these equalities, but generated by two elements R and S using these equalities. So, yeah. So you start with the free group generated by R and S, okay? And you've got all possible R's and S's and their multiples, well, not multiples, powers and things like that, okay? But then this is different from the free group, because you additionally, wherever you see r to the 6th, you just take it out, you replace it with the identity. Wherever you see two s's in a row, you take it out, you replace it with the identity. Okay? Wherever you see SRS, you replace it with r to the -1. Or you can do. So you have different strings of s's and r's that can give you the same element. And the way to tell which element it is using these groups. And such groups are called finitely presented groups. Yeah, well, if you wanted to do it more formally, you need to know a bit more formalism, which we're getting to later in this course, but for the moment, just take it as kind of an intuitive description of what they do, what they are. Okay. Well, the last thing. So just before, I mean, there is like a, I mean, it's a theorem 5. It's theorem 528. But it really is just, but really, an example. Rather than a theorem, is that the group of symmetries of a cube is S4. Okay, it's in the book. So I'm telling you. She's been reading it, haven't you? Okay, so the idea is that this is another deep kind of thing, is that S4 is acting on something. So groups act on things, and we'll see that later as well. But so you think of so what is S4? Okay, so it's not S4 really, but one should say isomorphic to S4. So for all purposes, it's as good as S4. Except what it does is, so when you look at the cube, okay, do we have a cube? The cube has 4 diagonals. Okay, you look at so for example, you can look at the top square, and from each vertex of the top square, you go to the opposite cross. Okay, so and then here. So you take these 4 diagonals. And now, any diagonal, you can, by a symmetry, by a rigid motion of the cube, you can go from any diagonal, you can get any permutation of these diagonals. So this is how it works. Read it in the book if you're interested. Not a particularly important example, it's just I think the whole point of what we did today is to see groups appearing as permutations of some mathematical objects that you come across earlier in your lives. So to kind of demonstrate the abundance of word groups that's not up here. Which, unless there are questions about this. So we've done these chapters 4 and 5 now, and Killian is starting chapter 6 next week, which means that we've got a bit of an easier lecture tomorrow. Well, and make it a kind of a tutorial. If you have been trying some exercises in chapters 4 and 5, and find some of them particularly intriguing that you would like to know more about, get your questions ready for tomorrow. If not, then we'll just go through them as they are there, I think, in this chapter 5, and see if we can solve them here all together. All right?
Yeah.
Good. So that's it then. See you tomorrow.